Good morning to you, my dear students. There are 8 students, so shall we start the lecture? Are we to wait for the others? Okay. So we'll do stability of latex today. I hope you all went through the material that we covered last time, and we will do 2-hour lecture today as a cover-up of last week that we couldn't do due to faculty board meeting. Okay. Can you all see the screen? Pasindu, can you see the screen?
Yes, madam.
Okay. So last time we talked about latex as a colloidal system and what are the colloidal properties. And we talk about Brownian motion and Tyndall effect in detail. Okay. After that, we talk about how colloidal systems are destabilized. And we talk about natural rubber latex as a colloidal system and how instability may occur in latex under normal natural setting. Okay, so today we will be doing, we did preservation also, right? Dilshi, you were there last time. We did preservation, right?
Yes, madam.
Yeah. These questions, did you all do? I hope you all have answered these questions. If you have any hard position or anything you don't understand, you can ask after the lecture today. We will have a small discussion. So today we will be doing stability of latex when we think about latex as a colloidal system. Okay, now last time we talked about different types of colloids and we learned natural rubber is a lithophobic colloid. Lithophobic colloid means, what is the answer? If anybody remember? What is the lithophobic colloid? We learned about lithophobic colloids last time. Chamira was there last time, right? Look at your note and tell me what is a lithophobic colloid. This is lithophobic colloid. You have a hydrophobic hydrocarbon chain dispersed in a polar solvent. So the particle is hydrophobic, solvent is hydrophilic or polar. These are two immiscible phases stabilized in a colloidal system. So if dispersed agent and dispersing medium are immiscible, we call it leophobic colloidal systems. Okay, don't forget it next time. You have to remember this, right? If the dispersing agent and dispersing medium are in two different immiscible phases, we call such colloidal systems as leophobic colloidal systems. I hope you will remember it next time. So in stability of leophobic colloids, you need to persist the stability of this immiscible system for a longer period of time. Then we call this leophobic colloidal system is stable. Okay. Now, under normal circumstances, when the particle is big, the leophobic systems are thermodynamically unstable. That means under thermal conditions, under normal conditions, these two phases tend to separate, like oil in water system. Okay, oil will be separated into two different phases under normal environmental conditions. But when it is made into an emulsion, like peanut butter, or if you take that foam cream, the cream in cakes, all are stable for a longer period of time because they have made into a leophobic colloidal systems. So this leophobic colloidal systems actually under colloidal circumstances, under natural environmental conditions, you can keep it for a longer period of time. This stability usually depends on the free energy, interfacial free energy. Now we are coming to little scientific terms. Interfacial free energy or surface tensions. Surface tensions, you all know. Have you learned about surface tension in A level? Yes, right? Under science for technology, you all learned about surface tension. Now, you need to talk with me, otherwise how can I do the live lectures? Surface energy, surface tension, do you all know? Dilshi, do you know surface energy, surface tension?
Yes, madam.
Okay, so this is the same as surface tension. High interfacial free energy, that means you have higher surface energy. This is occurring because of this small size, you have more surface, so there will be more forces acting on surfaces, interface between the hydrophobic part and the hydrophilic part. That is the surface of the particle. When the particle size is very small, the surface tension of interfacial free energy is very high. So this make high ratio of interfacial energy to volume of dispersed phase. So when you have higher interfacial energy, it will be staying as particles as itself. So this is what we say for the stability of hydrophobic colloids in scientific words. Okay, in normal words, if we say the surface tension, when you have soap, what happened? Soap bubble එක කොච්චර වෙලා තියෙනවද? ගොඩක් වෙලා තියෙනවද? වතුර බබල් එකක් හදනවට වැඩිය වැඩිද අඩුද? වතුර බබල් එකක් හදලා තියෙනවට වැඩිය සබන් දැම්මහම සර්ෆස් එනර්ජි එක වැඩි. ඒ වගේ වැඩක් තමයි මේ වෙන්නේ. එතකොට කෙන ගතියෙන් ගොඩක් වෙලා තියාගන්න පුළුවන්. මේක ඊටත් වැඩිය පුංචි droplets හදන හින්දා මේක ගොඩාක් වෙලා තියාගන්න පුළුවන්. That is what it says. So once the free energy is lowering, aggregation, flocculation will occur. Aggregation කියන්නේ මොනවාද? Particles එකතු වෙනවා. එකතු වෙනකොට surface එක මොකද වෙන්නේ? අර පුංචියට තිබ්බ surface එකක පුංචි particle එක තියෙන ලොකු surface area එක particle එක ලොකු වෙන surface එක අඩු වෙනවා. bulk volume එක වැඩි වෙනවා. bulk volume එක කියන්නේ මොකද්ද? surface එකට ඇතුලේ තියෙන volume එක. එතකොට මේක aggregate වෙනවා. මේක aggregate වෙන්න පටන් ගත්ත ගමන් වැඩිපුර වෙලා particles ගොඩාක් flocculate වෙනවා. all come together and this one is thermodynamically favorable. So what happened? Separation will occur. Layer separation will occur. Okay. So now we'll see what are the forces that will keep the heliophobic colloids in its place. Okay, so these forces are same as leophobic. Now, in the case of natural rubber latex, we said it is a leophobic colloid. The stability of latex is also depend upon the factors or attractive repulsion forces that will keep a leophobic colloidal system stable. So there are 5 forces acting on leophobic colloidal particles. So these leophobic colloidal particles are attracted using van der Waals forces. Electrostatic repulsive forces keep them apart. Then we have steric repulsive forces that is also keep the leophobic colloidal particles apart. We have solvation forces and depletion forces that is also called as exclusion forces. So there are 5 interparticle forces exist in between leophobic colloidal particles. So when I say leophobic colloidal particles, it is similar to rubber particles as well. Anything you didn't understand, you can unmute and tell. තේරුම් නැති දේවල් තියෙනවා නම් අහන්න. Okay, I will pause the recording for a while. So these 5 stability forces, first one is van der Waals attractive forces. As I said before, if the particles needed to be in stable position, there should be a attractive force acting upon different particles. So Attractive force basically is van der Waals attractive forces. These are very small compared to other types of attractive forces acting on molecules. Harita, I hope you understand. The other attractive forces are like ionic forces, covalent bond attractive forces. These are very strong attractive forces. But in the leophobic colloidal system, we have van der Waals attractive system. This is smaller compared to the other bonding forces. Second type of interparticle force exists in leophobic colloidal systems are electrostatic repulsive forces. Now, as I said before, when we discussed about the latex particle, we said on the latex particle, there are proteins, and these proteins are negatively charged. So altogether, when you think about the latex particle, it is negatively charged. It has a negative charge surface. Okay. So when two particles of such is brought together, what will happen? The negative charge on protein will repel the negative charge on the other particles so that the particles will not come more closer due to van der Waals attractive forces. Now, because of these two forces, these will be counterbalance and be stable. Other than these two, we have steric repulsive forces, solvation forces, and depletion exclusion forces. All these 5 forces act upon leophobic colloids so that these colloidal systems will be stable in the colloidal form. Okay. So we'll go to electrostatic stabilization. In electrostatic stabilization, you have a ionic surface. What is the ionic surface here? What is the ionic surface in latex particle? Chamira? Chamira? Now what is the
minus charges?
Yeah, what is the minus charge? What is it arises from?
A protein layer.
Okay. So protein layer will give rise to this minus charge surface. So this minus charge is the one that responsible for electrostatic stabilization of latex. This is due to bound electric charges. Bound means the protein bound to rubber particle having negative charge will repel each other. So this ionization chemical groups on the surface, we could repel each other. Other than that, we have adsorbed charge species on the particles that we will be discussing under surfactants, where when you put the particle into a medium, there are different molecules in the medium. They will tend to adsorb. This is not chemically binding, just physical attachment of different chemical species onto the surface will also give rise to electrostatic stabilization that is not in latex but in other leophobic colloidal systems. For example, if you have water in the medium and your particle is positively charged, what happened to water? H plus is there, O minus is there, so O minus will attract onto plus charges on the particle if there are plus charges. Okay, if there are minus charges on the particle, H hydrogen atom side, that is slightly positive charge, will come and attach to negative layer, which give rise to another second charge layer that also act to stabilize the particles. Now, when you talk about electrostatic stabilization of latex, discussing about proteins is more than sufficient. Okay. The other factor that I talk about is for the other types of latex, you have synthetic latex and all types of different colloidal systems. They are stabilized by the second point that I was talking about. Understood? Anything unclear? Until I ask your name, don't stay. If you don't understand, anybody can ask. Do you understand what I'm talking?
Yes, madam.
Okay, very nice. Okay, so this is protein one. When you write in your answers, remember when you write in your answers, you have this, you have to use this diagram. Okay. Now this diagram, you have to draw it where you have to show inside the core, you have polyisoprene chains. Onto the polyisoprene chains, you have the smaller particle is phospholipids. Pinky particles are phospholipids, and the green particles represent proteins. And here on protein, you have negative charges. Okay. And when negative charges are there, the rubber particle, this negative charge on proteins will give the rubber particle a net negative charge. Okay. Right? When you write, you have to write in natural rubber latex particle. The lipoprotein layer on rubber particle gives a negative charge. Draw this one and say this one in word. So this negative charge protein layer will help to stabilize the latex via electrostatic repulsive forces acting between two negatively charged surfaces. Okay, because negative charge protein or negative charge particle repels another negative charge particle so that they will avoid two latex particles to be attracted together and avoid aggregation. If the electrostatic repulsive force is enough to avoid aggregation, then there will be no flocculation, no coagulation or coagulation until this protein layer is damaged. We have learned in previous lesson that what are the factors that degrade proteins and remove the proteins from this surface. Okay, we'll come to the second type of stabilization, that is due to steric forces. Again, as I said, steric forces are repulsive. The steric means bulkiness of groups. If you have a bulk group on the surface, can another particle penetrate through this bulk group? Now, ඔයගොල්ලෝ හිතලා බලන්න අපි සාමාන්‍යයෙන් ටිකක් සෙල්ලම් කරනකොට අර මීයයි පූසයි එහෙම නැත්නම් මොකද කොපර පිපිඤ්ඤා එකේදීන් අපි කරන්නේ මොකද? ඇතුලේ එක්කෙනෙක් දාලා වටේ වලල්ලේ අපි ප්‍රොටෙක්ට් කරනවා සමහර වෙලාවට ලං වෙලා ප්‍රොටෙක්ට් කරගන්නවා සමහර වෙලාවල් වලට ටිකක් ලොකු එක්කෙනෙක් දාලා ප්‍රොටෙක්ට් කරගන්නවා ඒ වගේ ටිකක් ලොකු කෙනෙක් දාලා ප්‍රොටෙක්ට් කරගන්නකොට තමයි ස්ටෙරික් ස්ටැබිලයිසේෂන් එකක් කියන්නේ. දැන් පුංචි රවුමක් වටේට ටිකක් ලොකු මුද්දක් දැම්මු. මුද්ද බලන්න. වටේටම ගල් අල්ලනවා. ටිකක් ලොකු ඒවා. ලොකුම එක හරහා එන්න ඕනේනේ දෙවැනි එක නේද? ලොකු ගලක් අල්ලලා පුංචි ගල් ගොඩාක් ඇල්ලුවත් ලොකු ගල පාස් කරන්න ඕනේ ළඟට එන්න. අන්න ඒ වගේ group එකකට තමයි steric stabilization එකක් කියන්නේ. So when you protect the surface with adsorbed bigger molecules, the same repulsion will occur. Okay, so in the presence of adsorbed molecules on the surface of the particle, which are very big, you will protect the particle against getting together. ලං වෙන්න බෑනේ නේද? එළියේ තියෙන ලොකු එකක් තියෙන හින්දා ඇතුලේ තියෙනවට ලං වෙන්න බෑ. ඒකට මික්ස් වෙන්න බෑ. So this is called steric stability, but this is the simplest way of teaching this one. There are some other chemical aspects in it, but just I hope you understood the stabilization. Now this usually occurs due to adsorbed polymer particles on the surface or use of surfactants. වටේට ටිකක් ලොකු ඒවා තියෙද්දි මේ වගේ loops එහෙම තියෙද්දි අපේ particle එක ලොකු වෙනවා. හරි? voids එනවා ලොකු වෙනවා. එතකොට ඇතුළට එන්න බෑ. So this is the schematic representation of the adsorbed polymer molecules on a plane interface, so that you cannot pass through this barrier. From here onwards, you cannot pass. So in order to mix with this one, it's difficult. Do you understand? So this usually comes with the non-ionic polymer lattices. So if you want to read more, take your reference book. Anyway, I should ask you to read this one. We are reading for a degree now, so you have to go to the internet, download the polymer lattices by Blackley. I think it is in volume 3. Volume 1 or volume 3. But volume 3, you have this non-ionic polymer lattices. Under this one, you can read it and understand. Okay. So this is a little bit more scientific words. Okay. In steric stabilization, you have entropic interactions and mixing interactions. Okay. In simple terms that I explain, entropic means loss of configurational entropy of polymer molecules on approach of second particle. Configuration එකක් කියන්නේ, now in the polymer you have cis configuration and trans configuration. So if the configuration is changing due to approach of the second particle, then there will be entropic interaction. So this part I will omit it, but if you want to read this one, you can take the note. There are two interactions under steric stabilization as entropic interactions and mixing interactions. Let's go. Just keep this one as your note. Okay, if you don't understand, you can still talk to me. Right, third one is stability by solvation. Now, solvation how can I put it? Now, in the case of a polymer particle, there are some ends of the polymer which is migrated outside the barrier. What is the barrier in the latex particle? That is phospholipid and protein layer. Through this one, there are small possibility of leaking out some ends of polymer chain. So when this polymer chain is interacting with solvents, then again there will be stabilization. Now mainly here again we talk about that water molecules absorb onto the surface when you have the full negative charge on the surface. Positive charges on water molecule, that is hydrogen plus, will orient towards the negative charge surface and have a physical binding which is much more intense than a normal absorption, but a little bit more because you have negative charge surface and a positive charged particle. You have a little bit higher forces, not as much as ionic force, but a little bit lower. So such force could keep a layer of water around the particles. So this is called hydration layer or hydration sheath. But similar to this one, we can have other solvents also arranged onto the particle of latex as a partially immobile layer. If you have such a layer, again, when you have two particles approaching together, they have to pass that solvent layer also. Immobile, partially immobile, so they will not detach as simple as approaching. Okay? It should have a bigger collision in order to repel those partially immobile solvation. So if you have solvation, again, it will be acting as a secondary stabilization or secondary protecting sheet. So this again have a stability against aggregation and flocculation. All these things are coming under interfacial energies and interfacial interactions of colloidal particles. So this is how usual colloidal particles, even if it is a nanoparticle, you have these 5 types of forces to keep them in colloidal position. All these forces are becoming big because of very tiny particle size. When you have a bigger particle, the volume of particle is bigger. The solvation layer or the radius of this hydrogen water bonded onto the particle will be comparatively small. Okay, podi particle එකක් තියෙනකොට වතුර වටේට බැඳිලා තියෙන layer එක ඇතුලේ තියෙන එකට වැඩිය ගොඩාක් ලොකුයි. ඒ හින්දා අපි comparatively හිතලා බැලුවොත් ලොකු particle එකකදී මේ molecule එකක් නෙමෙයි තියෙන්නේ. molecule එකකින් හදන layer එක ප්‍රමාණය එකමයි. ඒ වුණාට ඇතුලේ ලොකුයි. එතකොට සාපේක්ෂව forces අඩුයි. හරිද? ඒ හින්දා තමයි අපි ලොකු particle එකක් හැදුනහම සාපේක්ෂව තියෙන force එක අඩු වෙනවා. එතකොට දෙවනි particle එකට ඇවිල්ලා අර bulk ලොකු particle එකට attack කරන්න හරි ලේසි වෙනවා. පුංචි වෙන්න මේ තියෙන forces තියෙන ප්‍රමාණය එකමයි. හැබැයි ඇතුලේ තියෙන අර මේ particle එකේ size එකේ පොඩිකම හින්දා act වෙන force එකේ ප්‍රමාණය වැඩි වෙනවා. තේරුණාද? එතකොට මේ පුංචි particles තමයි solvation එකකින් stabilize වෙන්නේ. ලොකු ඒවා නම් එහෙම වෙන්නේ නැහැ. ලොකු වෙන්න මේ forces weak වෙනවා. මේ forces weak වෙන්න aggregation වැඩි වෙනවා. ඒකින්ද තමයි අපි කියන්නේ once the aggregation starts, it will multiply the process and comes to the coagulation state. තේරුණාද? නම කියනකම් ඉන්නේ නැතුව තේරුණා නම් තේරුණා කියන්න. participants ලා 6කට බහැලා තේරෙන්නේ නැති වුණොත් විභාගයට ලකුණු අඩු වේවි. Even we are going to get bad impression of we are not teaching you all. Pasindu, do you understand? Namai panahai. මේ අඩු වෙන එක නම් ලයිට් නැති හින්දා අඩු වෙන එකක් නෙමෙයි. පසින්දු
मैडम
තේරුණාද?
मैडम मैसेज लॉग आउट ना දැන්ටිට කලින් කරන්ට් එක ගියානේ මේක
කරන්ට් එක ගියේ කීයද?
මේ
කොහොමද අනිත්
හොස්ටල් එකේ කරන්ට් නැහැ
හරි ඉතින් ඒක මම අපිට අල්ලන් ඉන්න බෑ. But anyway, you all have mobile phones, right? You have only 2 lectures today, na? Right. Anyway, ask the others to come. If not, only these 6 students will score. Where is Pasan? Dilshi, where are the other girls? Sachini is there. Minoshi is there. What happened to the other one? I'm asking you all questions because I want to know whether you all understood it so that I could go. Okay, next one is depletion stabilization. And now, in the case of depletion, polymer particles will be dispersed into the solvent. So this is called depletion. And due to this depletion also, there will be stabilization occurring. This stabilization is called depletion stabilization. So these are the 5 forces or 5 factors that affect stability of the colloidal system. So when I ask you 5 factors, state 5 factors affecting the stability of natural rubber latex, it has to be said Van der Waals attractive forces or Van der Waals stabilization, electrostatic stabilization, steric stabilization, and solvation stabilization, depletion stabilization. So these are the 5 factors that affect stabilization. Okay, when you go through the previous past papers, you could see such questions are there. So when I ask such a question, you should write this one, not only the electrostatic stabilization. If I ask you to explain 2 or 3, you need to know how to explain it. Okay? Don't write only electrostatic stabilization when I ask you what are the 5 factors. Okay? Understood?
Excuse me, madam.
Yes?
Madam, මෙතන free polymer එකක් dissolve වෙලා තියෙද්දි ඒක කොහොමද stabilize වෙන්නේ?
හරි. රම්බුටන් ගෙඩියක්. ලොවි ගෙඩියයි. සයිස් එක එකද නැද්ද?
වෙනස්.
මොකෙන්ද වෙනස් වෙන්නේ?
අර කූරු කූරු තියෙන රම්බුටන්.
right. රම්බුටන් ගෙඩියේ කූරු කූරු තියෙනවා. නැතුව ඇතුලේ තියෙන එක එකම සමානයි නේද? එතකොට රම්බුටන් ගෙඩිය අපි ස්ටැක් කරනකොට ඒක ලං වෙන්න පුළුවන් දෙකට එකට. ගෙඩියේ මැදේට ලං වෙන්න පුළුවන්.
බෑ.
බෑ. ලොවි ගෙඩියට
පුළුවන්.
ඒක තමයි මේ. dissolve වෙනවා ඇතුලේ තියෙනවා පොඩ්ඩක් එළියට ආපුවාම මොකද වෙන්නේ? අර රමුටන් ගෙඩිය වගේ තමයි. ලං වෙන්න පුළුවන්. බෑ. මේකේ දැන් පොඩ්ඩක් එළියට deplete වුණාට these are all stabilized by other forces like hydration or solvent attraction. There are some other additives present in the latex like proteins, dissolved proteins. So all these will attach onto this. So coming together is a little difficult than without depletion. But once you deplete it, the removal is also difficult. That is another point. That also I will teach in another point. දැන් තේරුණාද? අනේ රමුටන් ගෙඩියේ structure එක තමා මේ deplete වුණාම පුංචි particles නේ මේවා. මේවා ඇහැට පේන්නේ නැති particles අපි මේ කතා කරන්නේ. ඒකට මේ particles එකට එකතු වෙන එකත් අර වගේම තමයි. හරිද?
හරි මැඩම්.
Okay. Now, in our previous lecture, we talk about destability or instability occur under normal environmental conditions. That is, what is it? Spontaneous coagulation or putrefaction. Now, even if your latex is not disturbed by the presence of natural factors, there are some other factors influencing destabilization of natural rubber latex. Okay, now in the case of destability, again you have different factors like agitation. Agitation is when you apply a force to agitate or mix together. Like if you transport latex from one place to another for a longer distance with high agitation, these latex tend to coagulate. Okay, so the physical influences that affect stability of latex are, one thing is agitation. Second one is heating. Excessive heat will destabilize natural rubber latex. Other than heating, freezing also destabilizes natural rubber latex. Now, other than these three, you have sunlight, ozone also. Okay, mainly agitation, heating, and freezing will destabilize natural rubber latex. Okay. Now, under this one, first one is agitation. Now, agitation means, in other terms, we call it mechanical stability of latex. අපි මොනවා හරි force එකක් දීලා stir කරලා shear කරලා ගන්න latex එකේදී stability එක අඩු වෙනවා. මේක for transport, it is one crucial point of transporting and also storage. Third one is film forming ability is going to be very much drastically the film forming ability drastically decrease if you don't have enough mechanical stability. Okay, so usually along with the time, that means when you store the latex over a period of time, the mechanical stability of latex goes down. Now, in the case of producing different goods, you need to have all types of movements like dipping, stirring, all are agitational modes. Okay, if the latex is unstable during the processing, you will not be able to produce different goods out of latex. So, stability of latex is important under agitation. Now, how do you destabilize the latex? How do you explain the destability of latex due to agitation? Now, when you agitate or mix in violent forces, what will happen to the particles? They will collide each other in high force. Due to the movement of the latex particles under agitation, the particles will collide in bigger force. This force is sufficient for the particles to get together and form a bigger particles. Once you form the slightest bigger particle, that is aggregates, the second, third process is very easy. Flocculation, coagulation, and coagulation. I always use these 4 words, okay? First, aggregation. Second, flocculation. Third, coagulation. Fourth one is coagulation. Okay, that is the series of particle sizes getting bigger. So this, in order to measure whether your latex is under processable conditions, you need to test the latex. You'd make use of mechanical stability time in order to test whether your latex is in a good condition for product making. So this MST, you can see the picture here. Okay. This is the mechanical stability tester that we have in our lab also. This is not the same brand here. I took it from internet. This is the mechanical stability tester. It's very simple procedure. Now here you have a shear rod. පුංචි rod එකක් තියෙනවා. ඒකේ යට මේ තියෙන්නේ පුංචි disk එකක් තියෙනවා. මේක immerse කරනවා latex එක ඇතුලේ. Okay. After immersing, you give a constant shear or rotation of 14,000 RPM until it approaches the endpoint. Now, what is this endpoint? I will come to it a little bit later. That is when the latex becomes unstable, you get the endpoint. Usually, you can determine it by hearing the sound. The stirring sound will give you a different sound. And also, the meniscus of the latex goes down. Why? Particles are getting aggregated. And also, turbulence is also getting lost. So when you see all these observations, you can get the endpoint, but I will show you in the lab when it comes to the lab how to measure mechanical stability by the use of this equipment. So when we talk about the quantity, the time, that means endpoint, the time reached to endpoint. If the time is longer, then latex is more stable. So it needs more force to coagulate. That is what it says. MST is longer means you need to give more force to coagulate the latex. But when it comes to latex products, we have an optimum time that, of course, I will teach you under maturation. Okay, so the standard test method for MST, we have test methods for latex as ASTM. ASTM D1076-06 ISO 35 2004. So these are the 2 standard test methods. You can download it from internet. And usually for a good latex to be processed, MST is around 450 to 800 seconds at 14,000 RPM. Okay, this is a simple one. Now let's see what are the what is the difference between latex. Now you can see before MST you have a nice white color solution, and under MST you have tiny clots form in the same latex after MST is reached. The endpoint could be determined by first appearance of these small clots or coagulated rubber. So when you reach the time, you note down the time and give another 15 seconds additional rotation, then you could see bigger particle sizes so that you can stop and take the previous reading as the endpoint. So usually when we talk about the endpoint, it is 1% of the coagulum based on total solids is needed. You can determine it, and as I said, this is a time, mechanical stability time. So MST is determined as a number of seconds. It's not minutes, just seconds. 450 seconds means how many minutes? Quickly calculate and tell me how many minutes 450 to 800. Gana hadala kiyan. Hiroshima, tell me the time in minutes. For better latex, we say 450 seconds to 800 seconds is the good MST value. 450 in minutes. Hayo, mechir velane. Hiroshima, Sachini. 450 seconds means how many minutes? Pasindu. Are you there? Pasindu, what is 450 seconds in minutes? Okay, Chamira, what is 415 minutes?
7.5 minutes.
7.5 minutes. This what is 800?
13 minutes.
Yeah. Others, are you in the class? Hiroshima, Sachini, Minoshi, are you in the class? Or have you logged and gone somewhere else? No answer. Very bad. The other two? Thank you. It's good.
Yes, madam.
Okay. So now we'll move into the second point, that is during freezing, what happens to the latex. Now, in the case of freezing, water, you have latex dispersed in water. So during freezing, this water will be freezed up and make ice crystals inside latex. So the ice crystal starts growing up. What happened to the latex particle? Tend to reject from the ice crystals. Once the ice crystals are made, these ice crystals reject the latex or the rubber particles so that the dispersed phase and the particles concentrate in different regions so that it is forced the latex particles to be coagulated. Too much coming, these ones are solid. So when the solid starts to grow up, the lattice, crystal lattice, force the particles to get together and form a bigger latex bulk. So this causes coalescence. Once you freeze, the latex will not return to the latex phase even if you heat it back, because they are already coagulated inside. Okay, so when you transport or when you store latex in different places, you have to remember, if the latex is frozen, you will not be able to get the latex back as it is. It's just solid rubber. Okay, so next one is heating. What happens in heating? Heating, water will evaporate. Slowly, water will evaporate, making the latex concentrated. Then what will happen to latex? Only rubber will be remaining in the phase and all the water molecules have escaped. So it will become dry rubber. So these are the physical factors that destabilizes latex. Remember, due to agitation and freezing, you cannot make it reverse. And if the latex is heated further into a point, after that point also, you cannot use the latex because it's already becoming dry rubber. Due to heating, it will form a nice film out. So these are the physical factors that influence stability of latex. Now I said, when you expose latex into sunlight and ozone, again it destabilizes. That destabilization occurs due to degradation of polymer molecules, removal of double bonds due to different reactions. So that is different from physical influences. That is, chemical influences occur under ozone-rich environments, and sunlight deteriorate the structure. So that is how the other two factors affect. So basically, if I ask you what are the three factors affecting destability under physical influence, that is agitation, heating, and freezing. Okay, so all three I have already discussed with you. So you should know the mechanisms of destability. තේරුණාද?
madam freezing එක ආයෙත් පැහැදිලි කරන්න පුළුවන්ද ටික?
Now in freezing, මොකද වෙන්නේ freeze වෙනකොට? අපේ system එකේ තියෙන්නේ, you have small rubber particles dispersed in water. Okay, water, there is bulk water inside, right? You have 35% of rubber or 60% of rubber in 65% of water or 40% water. Okay, in two different systems. In fresh latex, you have 35% of rubber particles dispersed in water. So there are a lot of water in it. When water starts freezing, the water molecules get together and form crystals. Make crystals, එකින් එක එකතු වෙලා හොඳ lattice එකක් හදනවා. ලොකු crystal එකක් හදනවානේ. මේ crystals හදනකොට වතුර විතරයි crystals හැදෙන්නේ. එහෙම නැතුව ඒකේ තියෙන dispersed particle එක crystal එක ඇතුළට යන්නේ නැහැ. එහෙමනේ. නේද? අපි ඔගොල්ලෝ මේ crystallization ඉගෙනගෙන නැද්ද chemistry වල? practicals කරලා නැද්ද? අපි ඕනෑම solvent එකක දැන් හිතන්නකො ලුණු වතුරේ තියෙනවා කියලා. ලුණු ටිකක් concentrate කළ වතුරේ තියෙනකොට වතුර මේ ලුණු කැටේ ඇතුළට යනවා. crystal එක හැදෙද්දි. නෑ නේද? අපිට එළියට ගන්න පුළුවන් ලුණු කැටේ පිටින්. අන්න ඒ වගේ වතුර freeze වෙනකොට ඒ කියන්නේ එයා solid වෙනවා. මේ solid එක ඇතුළට dispersed phase එක රිංගන්නේ නැහැ. මොකද වෙන්නේ? pure වතුර තමයි crystallize වෙන්නේ. එතකොට crystal එක හැදෙන්න මොකද වෙන්නේ? dispersing medium එක. එයා solidify වෙනවා. rubber particle එක තල්ලු කරනවා. තව crystal හැදෙනකොට තව particles තල්ලු වෙලා අයින් වෙනවා. එතකොට මේවා regions දෙකකට concentrate වෙනවා. ඒක මං කියන්නේ physical regions දෙකක් කියලා. ඒක phases දෙකකටයි වෙන් වෙන්නේ. එතකොට මේකේ පොඩ හැදිලා ගොඩාක් ice crystal එක හැදීගෙන යනකොට ඒකවර ඔක්කොම ටික freeze වෙලා යනවනේ. මේ වගේ cavities ඇතුලේ ටිකක් ලොකු cavities ඇතුලේ rubber particles force වෙනවා. මේක force වෙන්න මේගොල්ලෝ ice වෙන වෙන් වෙනවා. rubber එක වෙන් වෙනවා. ඒ කියන්නේ layer separation එකක් වෙනවා. layer separation එකක් වෙනවා කියන්නේ coagulate වෙනවා. මේ coagulation එක ආයි හරවන්න බෑ. අපි වතුර දිය කරලා ගත්තා කියලා layer separation එක වෙනස් කරන්න බෑ because it's already been coagulated. You can try this one at home even. Take some latex from a nearby field, put it in the freezer and check. You will see that one. Now, your senior batch might have noticed this one because one of our technical staff put the latex in freezer without knowing. We had to throw away 10 liters of latex due to that one. Because we cannot use it back again. We just could use it as a dry rubber latex. තේරුම් නැද්ද දන්නේ තාම. තේරුණාද?
තේරුණාද?
So this is today, coming to the end of today's lecture, but as I said, I will be doing 2 lectures together. Now here, under freezing, now thawing means heat back again, defrosting, the coagulum will be resulted and latex will not return to its original appearance. That is what I said before. Thawing means frozen latex defrosting. Okay, defrosting is different. Thawing is masse hema fridge එකෙන් අරන් එළියෙන් තියලා ice බහිනවට තමයි thawing කියන්නේ. අන්න ඒ වගේ latex එකත් freeze කරලා එළියට අරන් ice බහිනවා කියන එක තමයි thawing කියන්නේ. So this degree of coalescence increased by the time subjected to freeze and the temperature. If it is very low temperature, it is, of course, you cannot help it. Okay, now if you want to transport latex from one place to a very colder temperature, we should reduce this thawing, the coagulating effect. So usually, using a non-ionic surfactant could improve the resistance for freezing and thawing of latex, such as addition of ammonium laurate and potassium oleate, but this is found in a patent by Ritchie in 1966. Okay, don't ask me what is the mechanism. It may be because the particle is surrounded by ionic surfactants, so that during particles are getting into forced together, they might not react together because of this protective ionic layer that we will talk about in the next topic actually. Okay, so stabilization of natural rubber latex. That is what I was talking about just a few seconds ago. Do you understand up to this point? No questions means you understood. We will move on to the second topic under this section, stabilization of natural rubber latex. Now, this section means we could add different additives to improve the stability of natural rubber latex. The most common stabilizers that we could use for natural rubber are surfactants, fatty acid salts, or strong base compounds, such as ammonia. So we have already learned about fatty acid salts. So we'll mostly focus on surfactants in this part, okay? In surfactant, this is also known as a surface active agent. Okay, that means something related to the surface. Okay, surfactants, these are also soaps. Okay, surfactants are also soaps. Now, in the surfactant, you have two different regions in the same molecule like this. You have a polar head and a non-polar chain. So usually, non-polar chain is a hydrophobic tail, or this is like a tadpole. You have the polar hydrophilic head, which is having a water-loving part or hydrophilic part and a hydrophobic part in same molecule. So when you put such a compound into water, they could lower the surface tension. In other words, we can say it lowers the free surf-interfacial free energy. I haven't write it here. You can make a note. You can lower the surface free energy when you use a surfactant. I'm not that fast. You can take down notes. If you don't take down notes, you might not be able to write the exam, okay? So when you have a polar hydrophilic part, we'll see how this happens. Now, when the surfactant is added to water, now here you have the surfactant like this. You have a polar group and a hydrocarbon chain. Put it into water. This surfactants arrange into this ball type shape so that hydrophobic part will be coming inside. This is spherical, okay? This is just a cross section like a ball. Inside the ball, you have the hydrophobic chain, and outside you have the hydrophilic head, so that this will minimize the hydrophilic repulsive effects. So this type of a ball, we call it micelle or micelle. Some people say micelle, mostly in American pronunciation, it is micelle, or in European pronunciation, this is called micelle. So this micelle will be formed in dispersing medium. Now, what happened if the dispersing medium is different? If you put it into oil phase, what will happen? Inside will be the polar head groups will arrange inside and hydrophilic tails will come out. So in either way, these surface active agents could stabilize if you have two different immiscible particles in it. So if you have an aqueous phase, a hydrophilic particle dispersed in oil phase, the micelle is formed in this way and stabilize. So if you want to prepare any colloidal systems, like if you want to add an oil into latex, which is always when you add an additive, it is in bulk, bigger particle size, so they will tend to repel. So if you want to mix them, you need to add a surfactant so that it will have this type of a micelle arrangement, protected and form a stable dispersion. So you can use such surfactants for stabilizing latex as well. But before going on into stabilization of latex, there are 4 types of surfactants which are classified according to the nature of this head group, hydrophilic head group, and such as anionic type, cationic type, amphoteric type, and non-ionic type. Usually non-ionic comes here, but for the easiness of understanding, I put anionic, cationic, amphoteric, and non-ionic type. In the anionic type, polar head group, you have a negative charge, or the ion is going to be negatively charged head. Cationic type, you have a positive charge head. Amphoteric type, you have a Zwitter ion. Zwitter ion means same molecule have 2 different charges together. Non-ionic is you have a head group which is hydrophilic, but actually they are not containing any cation or an anion or a Zwitter ion, just hydrophilic non-ionic type of a molecule. So there are 4 types of surfactants based upon the nature of the polar head groups, that is anionic, cationic, and cationic, amphoteric, and non-ionic type. Now, thinking about the structure of latex particle, what type of surfactants can you use for stabilizing natural rubber latex? You know the structure of natural rubber latex. Draw it and see which type of a surfactant could be used in order to stabilize the latex using surfactants. This is one crucial point. We add surfactants to latex when you produce all the different products. You need to have this. Draw the latex particle and see what type of surfactants could be used among these 4. So these are some examples of surfactants used in different industries. Anionic one, you have alkyl soft sulfate, soaps, Calsoft, Texaphone. This type of surfactants are used in laundry detergents, dishwashing liquids, shampoos. Cationic ones, quaternary ammonium salts, used together with non-ionic surfactants, usually not with anionic softeners in textiles, anti-static additives. Non-ionic, usually ethoxylated aliphatic alcohols, polyoxyethylene surfactants, Triton X100, Span, Surgitor. So this type of non-ionic ones are using as wetting agents in coatings and food ingredients. Zwitter ionic or amphoteric ones, which are beta ions, amphoacetates, these are usually expensive and they have special uses, for example, in cosmetic industry. So did you come up with the answer that I have asked you? What type of surfactants among these four could be used as stabilizers in latex industry? Okay. So I think you all have came across now, you can use non-ionic or anionic type of surfactants to be used as latex stabilizers. Usually the anionic types are sulfonate, sulfates, or carboxylate based surfactants. For example, potassium lauryl sulfonate. So that the surfactant group is lauryl sulfonate. Sulfonate is a negative charge one, and the other one is potassium lauryl sulfate, potassium sodium dodecyl sulfate. Also, you have potassium dodecyl carboxylate, like a big chain and a negative ion head. Also, you can use non-ionic based stabilizers like Triton X100, fatty alcohol ethoxylates. Such type of non-ionic ones also could be used. So only these two could be used for stabilization of latex. Other than that, we cannot use any other, like zwitterions. They are expensive, or even we are not going to think about it to use. They are not stable. And cationic type also we don't use. Usually the stabilization of latex can be maintained by electrostatic repulsion on the surface of the rubber particles. So it will prevent flocculation of the molecule. In this way, you have the rubber particles suspended with low viscosity. When you add the surfactants, you have the this is a non-ionic surfactant actually. This red color one is non-ionic parts. This one will interact with the surface of the rubber particle, whereas the blue color one is hydrophilic part, will expose into water. So this type of stabilization, they will prevent coagulation or coagulation upon aggregation. So in under high viscosity even, they will not tend to join together or aggregate, mix together, prevent this one. So that is why I said non-ionic type of surfactants could prevent coagulation or coagulation during freezing. So such type of a one will have a protective layer that will avoid the particles getting coagulated. So this is how you do, how you prevent destability in freezing. And also when you have a latex which is mature, or the time has already gone, so the bacterial growth is there and depletion upon depletion of the protein layer, still if you have a surfactant layer on the top, they will not tend to mix because still you have a protective layer. This is hydration layer or micelle protection. Anyway, you have a protective coating around the latex particles so that it will not make it easy for coagulation to occur. So this is how you stabilize latex using surfactants. Now, when you talk about surfactants, there are wetting agents, dispersing agents, colloidal dispersion stabilizers, emulsifiers, foam promoters, foam stabilizers. as the ingredients that we use surfactants in latex industry. So with this, mostly I could finish this section. And we have to go to the next topic, Unit 3. I need another time to catch up the last week. So let me have a time so that we will finish it off. Any questions up to now? Do you have any questions? Under the next topic, that is latex compounding, we will discuss these things, okay? So don't worry about it here. And when we do the latex processing technology practicals, we will be using these things mostly in the next lecture module, that is designing and manufacturing of latex products. We will be discussing how to use different ingredients in detail with different products. If you have any questions, you can ask now. Okay, there is one more. I will stop the recording. So hope the others will stop the listening from here. Okay, stop.